Okay, let's keep going with this test review. A lot of conceptual ideas, I think, to cover on an exam like this. And these three questions here would probably be something like what I would expect to see. So question 210, what shape does a portion of a graph with a positive second derivative and negative first derivative have? So what is the shape of the portion of a graph where the first derivative is negative and the second derivative is positive? Alright, well, this part says it's concave up, okay, and this part says it's decreasing, so it's got to be decreasing, but it's got to be concave up, and taken together, those two ideas would give you a shape of a curve that's something like this. You can see it has its concavity up, but all of the tangent lines have negative slope, and that matches the criteria. In question 211, they say find the second derivative of this basic linear function and say what that says about the concavity of a line. So if I just have this line that goes through the origin and it has some slope k, then the second derivative of this will be 0. But it's 0 for any x, for any x value, for every x value, in fact. For every real number. So this tells us that, number one, there's no inflection points. Because in order to have an inflection point, not only must you be 0 at that x value, but you also have to change concavity there. And since there's no change in concavity anywhere, there can be no inflection points. And two, it is neither. It is neither concave up or concave down. At any value, right? It's certainly not going to be concave up or concave down at a particular point, because none of those points are because the second derivative is 0 for every point. So none of those points can be inflection points because it doesn't change concavity anywhere, and it can be neither concave up nor concave down anywhere because the second derivative is 0 everywhere. Question 212. If this here function is continuous and the second derivative is positive and the first derivative is equal to 0, then what must be true right at the point C? Right at the x value C So it would be the point C comma f of C. Okay, well, this just tells me that it's concave up, right? So it's upward shaped. And being 0 right there, just start off with the basic idea of what that tells you. It tells you that the tangent line goes horizontal right there at that point. If C is in the domain of F, then it would tell us that C is a critical value. And I'll presume that since F is continuous at C, that C is a critical value. Since in order to be continuous at C, you would need C in your domain. So C is a critical value. Maybe it tells you that there's a horizontal tangent line. Or actually, you know what this says? This says that this is that special interpretation of the second derivative test, right? If you check the concavity at a critical value, then you know if you have a local max or a local min. In this case, we have a local min. We have a local minimum at the point C, f of C. All right, so that would probably get us through all of the multiple choice questions for which there was 12. Okay, so then 4 more questions to go, and those are all going to be short answer. So let's start by looking at like this number 8. So suppose that the price and demand are related through the price-demand equation that's given here. Calculate E of P when P is 25. So let's just write down that price-demand equation. So it's X plus 200P is equal to 8,000. Okay, super. To have this become a D of P, a function of P, then I should solve it for X. So X would be 8,000 minus 200P. This is now a function of P. I can choose the price, I can put it right there, and it will tell me the number of units demanded at that price. And I can proceed with getting the derivative. That's easy. Okay, minus 200. And then just plug away at the formula for elasticity of demand. Remember that it starts off with a minus P. So E of P is minus P times D prime of P minus P times D prime of P over D of P. And when you plug in all of our stuff, we would get 200P over 8,000 minus 200P. And it would sure be nice if we would factor this thing just to have some smaller numbers to deal with. So you could write this as P over 40 minus P. And then it's also just as clear to do any number of things. The thing that they asked us to do in the question was to find what the elasticity was at the price of 25. And that would be, looks like it's less than 1. No, I'm sorry, actually, it's bigger than 1. Alright. So it is elastic at that price point. And if I wanted to know or how can I say this? So an even better question to ask is find P so that E of P is between, so that E of P is bigger than 1. Right? This is really what you want to be able to do right here. And stop that. Stop it. Stop it, kitty. As P, so observe that as P goes to 40, 440, as P goes to 40, you can see that E of P goes to infinity. And this would be going to 40 from the left. Stop! Stop chewing on my straw. Okay, so then which p-value is it going to take to make the numerator and denominator be the same? Well, that's just us looking at this thing and setting the top and the bottom equal to each other. So P needs to equal 40 minus P. If I add P to both sides, and then divide by 2, you can see that P would be 20. So then this gets satisfied. The demand is elastic for all prices between 20 and 40. And it's unit elastic right at 20. Okay. This cat is just into causing trouble this morning. Now let's look at, well, recall what this portion of E of P is telling us. This right here is exactly the relative rate of change of D, the demand equation. So if you want to discuss relative rate of change of some function, like if you are given a function and you want to talk about its relative rate of change, then you're needing to take the derivative of the natural log of that function, which is just to produce this guy. And follow your instructions. If it asks you to simplify, make sure you do. If not, then don't. Okay, so what would be a reasonable function for us to look at? Well, just about anything will do here, because I'm not framing it as a business type of question, so we'll just do number 6. The function is 8 plus 2e to the minus 2x. So my function is 8 plus 2e to the minus 2x. Then the derivative would be a minus 4e to the minus 2x. And my relative rate of change would be the minus 4e to the minus 2x over the original function. That's super easy. You can cancel a 2 everywhere, and you could factor out an e to the minus 2x. Is that really worth it? It's not required, so let's not do it. Just say minus minus 2e to the minus 2x over 4 plus e to the minus 2x. There you are. If I give you some curve, you're going to want to be able to find all of the extreme values, right, on a closed interval. Or if there's no interval stated, then it's on the entire domain of the function. Looking if there's one that I like from the review. Okay, number 20. Find the absolute maximum of x to the 4th minus 8x cubed on this closed interval from 0 to 7. So that function is x to the 4th power minus 8x cubed, and it's on the closed interval from 0 to 7. Alright, so there's my guy, and obviously need the first derivative, so that's going to be 4x cubed minus 24x squared, which factors like 4x squared times x minus 6. Yeah. Okay, so I know my critical values are 0 and 6. Okay, and then it's it's negative in this interval, but positive to the right of 6, and still negative for x being negative. This is the sign chart for f prime. Alright, so I know the function is decreasing and decreasing, then increasing. It made a 0 here, it made a 0 here, so I can see my local minimum right there at 6. I can see that local minimum. Alternately, you could take a second derivative and check the concavity at these critical value. And we're going to get that it's concave up at 6. So f double prime would be 12x squared minus 48x. So then f double prime of 6 would be 12 times 36 minus 48 times 6, and that's going to be positive. And so since it's positive, it's concave up when x is 6, so you know it makes a local minimum at 6. Now we're not done, because this is a closed interval that this function is defined on, and we need to know if how do we know that the function isn't doing something like, here's 0 and here's 7, and yeah, we found this local minimum here at 6, but how do I know that the function didn't, so we might go through this dot, but have some other minimum that's lower at one of the endpoints. Right? All I'm saying is we need to check the endpoints. You gotta check the endpoints. In fact, you need to check at the endpoints and the critical values. But I'm not gonna learn anything about using my critical value of 0 because it doesn't have a relative extreme right there, right? It has to change. It has to change from increasing to decreasing, or decreasing to increasing, in order to have a local extreme, and it does not do that at 0. So really, all I need to do is to find f of 0. Well, so this part of the graph I'm not even looking at. 0 is not even, really, to be a critical value, it has to be in the interior of your domain, and this is, so 0 is not truly 0 is an endpoint, it's not really a critical value. It's not in the interior of the domain. So the global extreme is going to be at 6. We're going to put 6 into f, and among these three numbers, the lowest one will be f of 6. You put those three numbers in, to that function f, and f of 6 will be the least such number. Meaning that you had a global minimum. It wasn't merely just, or absolute minimum. It wasn't merely just a local minimum. All right, and let's do one more, and then we'll be done. So there's one on here I know I want to do. Where is it at? The boat rental company. I want to do this boat rental company. Alright, the boat rental company charges its customers P dollars per day to rent a boat, where P is between $100 and $375. The number of boats rented per day can be modeled by the linear function given here. Okay, super. What is the maximum revenue, and how much should the company charge each customer per day to maximize revenue? So they have this function of P. They called it N of P because they are goofy. Let's just call ours D of P. Well, let me be careful, because that says the number of boats rented per day can be modeled by this linear function. I don't want to accidentally read too much into that. That just says the number of boats. Yeah, is the number of boats that can be rented as a function of the price. That's got to be the same thing as a demand equation. So they gave it to us like 1000 minus 4p on the interval from 100 to 375. So this is you can see that if they charged the minimum, if they only charged $100, it's a weird setup, but if they only charged $100, then nobody would demand any boat rentals. Weird. Okay. And so we should find E of P straight away. This would be this would just be 4p over 1000 minus 4p. And then I like to cancel those factors of 4. So that way we can just say P over 250 minus P. Then E of what equals 1. Well, that's going to be wherever P equal to 250 minus P is satisfied. So it looks like for P equal to 125. is where your revenue would get maximized. All right, and I think that's it.